Hello, we are Team 3. We will present our progress for the team project. We are planning to improve the paper cascade flight controller of quadrature based on deep reinforcement learning, which propose deep reinforcement learning based cascade flight controller for quadratures. Class DRA used single network for policy, which took long time to train, and the training process was complicated. But using the cascade form, the paper showed that the training process can be much easier. There are three main points in the paper. First one is the linearization of the quadrature dynamics. Second one is the cascade form of the controller, which was available due to the linearization. Last one is the hierarchical training process of the controllers. They first train roll, pitch, yaw, and G controller and use them in training X and Y controllers. Here is the replication plan. We plan to visualize the flight of the drone for the test and train the model using same method with the paper. After that, we are applying other algorithms from Stable Baseline 3 like PPO and DDPG to training controllers. We are done with visualization of the drone and train the model with original method. We also apply PPO to roll, pitch, yaw, and G controller. We are planning to apply PPO to X and Y controllers and apply DDPG to training controllers. For replication, we train the model using the same method of the original paper. We train the controller for roll, pitch, yaw, X, Y, and G with TD3. Left image shows the desired and drone position in the tracking test. Right video is the visualization of the flight during the test. And as you can see, the drone is flying along the desired trajectory. After finishing the training using the original method, we trained the model with Stable Baseline 3 library. We trained the roll, pitch, yaw, and G controller using PPO. We used the same observation, action, and reward of the original paper and only changed the training algorithm. After training, we compared the test result with the original method. For the test, we used the step target to check the convergence of the controllers. First, we trained the roll controller using PPO. We trained the model with 50,000 time steps. Original model shown steady state error and PPO shown the oscillation. After, we trained the pitch controller using PPO using same total time steps. Original model shown steady state error and PPO shown some overshoot. We also trained the yaw controller using PPO with same total time steps. Original method shown steady state error and PPO shown overshoot and oscillation. Lastly, we trained the G controller using PPO. Original model shown steady state error, but PPO shown good convergence.
And so for the current improvement, we have done three things so far. First, we modify reward function to reduce steady state error. Second, we change the attitude controller from idler angle to body angular velocity. And third, we augment additional state into the attitude controller to reduce the overshoot response. And for the first improvement, the modification of reward function. The original reward function takes the following form, where ET and ET-1 is the error between the current and the desired state in the current and previous time step respectively. And to maximize this reward, it implies that the error in the current time step should be less than the error from the previous time step, implying the improvement in the error, and also implies the reward is maximally converges to 0. However, this reward is also maximized if the values of ET-1 or the error from the previous time step is equal to the error in the current time step. And this implies the existence of the steady state error. And to reduce this steady state error, the reward function is modified as follows. And in this case, K1 is multiplied to the current error, and we also augmented the summation of the error term from each time step multiplied by the small values of K2. So the K1 term is introduced to guarantee that the error will converge in each time step when the reward is maximally converges. And the summation term is further introduced in order to correct the steady state error. And for the results, these two figures shows the plot of actual and target values of the zero angles of the original and the modified reward function. And it can be seen that the steady state error is reduced in the case of modified version of the reward function. Second, we change the attitude controller from Euler angle to body angular velocity. As in the original plan, we modify the attitude subsystem in the original source code from using Euler angles as the state to be using angular velocity. And so, lastly, we augmented the additional state in the attitude controller to reduce the overshoot. So after we change the attitude controller from using Euler angles to be using body angular velocity, we train that network for the attitude system. And from the original improvement plan, we plan to use only the error between the current and the target body angular velocity as the input, and the network will output the torque. But however, after we train the network, we observe that there is the overshoot in the results of the trained network, as can be seen from below figure. And so to reduce the overshoot, we augmented another state to the network, which is in which that network is the body angular acceleration of the drone. And we expect this augmented state to act as the D term or the derivative term as in PID control. And as there is no acceleration measurement in the pilot, we simply perform the Euler difference between the body angular velocity of the drone from the current and from the previous time step. And the result, as can be seen from the two figures below, they shows the it can be seen that the overshoot is reduced for the case of the two stages. And so in conclusion, we already replicate the results by training the network and by using the method in the paper, visualize the results using pilot simulation, and employ stable beta 3 library to use PPO algorithm. And we already improved by modifying the reward function, modifying the attitude system, and augmenting the state. And so for the remaining time, we will modify position system and compare the results with the original paper. And thank you for your attention.